All right. So on Monday, we left off at example number 10. I believe we were able to set up example number 10, which, just to refresh your memory, looked something like this. And so we were really looking for the first time at a sort of regular donut situation where we had an outer function and then we had an inner function. And so we had to consider that when we were finding the volume of our shape. And the way we did that was we found the larger radius and we found the smaller radius. And we were able to plug them into this formula, pi big R squared minus pi little r squared. And so what we're going to do right now is we're going to go ahead and go through about 3 more examples that are like this, okay, where we're looking at a situation where maybe these purple lines that we draw don't actually touch our axis of revolution. And so then we need to decide which one is our bigger radius and which one is our smaller radius, okay? So lots and lots of decisions here. So with that, let's go ahead and get started here. All right, so we're taking a look at another one that has a nice diagram here. Determine the volume of the solid obtained by rotating the region bounded by y equals 2x squared and y equals x cubed about the x-axis. And so one of the things we can start by doing is say, hey, we have this axis of revolution right here. So let's kind of mark that out. And if we wanted to color code so that our blue function right here is our 2x squared, I'm just going to go ahead and highlight this function in blue so we know that's the blue curve. And I'll highlight the y equals x cubed with the red so we know that's the red curve. Okay. Now, they give you the intersection points here. They tell us that these two functions cross at 2, 8, all right? But how would I, if I didn't have a graph, how would I find that intersection point just from the equations? What are our thoughts? How would we find the intersection point between two functions? Set them equal to each other, solve for x. Sure thing, let's do that. So we've got 2x squared equals x cubed, all right? And when we see this, we want to think, let's bring everything to one side, set it equal to 0. We'll go ahead and factor out. And we do indeed end up with x equals 0 and x equals 2 as our intersection point, okay? And so this point down here, we could label as 0, 0, because that's one of the other intersection points. Now, based on this graph and knowing that we're going to be revolving it around the x-axis, I bet our gut tells us that we should draw these purple lines. Let me zoom in a little bit. We should draw these purple lines sort of this way, vertically. All right, so here's sort of one. Here's another vertical one. Here's another vertical one. Okay. And so each one of those purple lines, that represents the distance between the big radius and the small radius, okay? Now, which one of these would we call the big radius? And which one of these would we call the small radius? What are our thoughts if we're revolving it around the x-axis? The red one is the big radius. And what's your reason for that? Why do we think that the red one is the big radius? Okay, I see two folks who are thinking the red one is the big radius. Why do you think that's the big radius? Because it's further from the y-axis. Oh, okay. I mean, it is further away from the y-axis, but our axis of revolution this time is actually the x-axis. So if you're comparing it to the y-axis, you might be thinking something like this, right? Lines that go this way. But our purple lines aren't horizontal, they're actually vertical, they're up and down. Okay, if it's not the red one, why do we think that the blue one might be the big radius? Like, what would our reason be? How do we know that that is a big radius? It has a greater distance from the axis of revolution. Yeah, exactly. So I like both of the reasons that I see here. It's farther away from the axis of revolution. That is very true. And it's sort of like longer. So when we sweep it around our axis of revolution, it's going to be wider out. Okay. And so this one we can say is the big radius. And this one, the y equals x cubed, is going to be our little radius. Okay. Now I intentionally kept that zoomed out so that we didn't necessarily have these other pictures on the screen. Okay. Now the reason for that is because I think it's important to practice looking at the diagram without all of the 3D pictures and kind of visualizing that for ourselves. Okay. Tell me a little bit more about that. What do you mean by, does it matter how steep it is?
It's probably gonna take me forever to type it out, but I was thinking like, say you're trying to get to one point, right? Usually people who walk straight versus or actually no, a curve is usually longer than going straight forward. Um so I thought like because of how different the steepness is, it could be like a longer distance. I
Oh,
could be
okay. I see what you're talking about, I think. Are you saying that like this arc right here is longer than the blue one?
it looks longer because it's like even though they're like at the same distance, it like you went more distance to like get to that part.
Yeah, so you are correct in that the red one has a longer, what we would call arc length, like it has a longer
Mm,
length than the blue one, but that length doesn't necessarily correspond to the location, like the distance from the uh, axis of revolution. So I could have like the blue curve and not have the red curve, and maybe I'd have like a red curve up here like this.
mm.
And if I had a red curve up here, which one is further away from the axis of revolution now? The red one that I just drew or the blue one that's y equals 2x squared?
The red one.
Yeah, that one has, I would say that the red one that I just drew is longer than the blue one.
Mm.
Okay. So really good observation in terms of thinking about like what could be connected to it. But we're really thinking if you have your axis of revolution, if you start from your axis of revolution and go towards the curves, the one that you encounter first, that's your little r. And then the one you get to second, that's your big R. Okay, so let me try drawing this again. I feel like it looks like a little worm, but so from my axis of revolution, I'm going to go up what curve do I hit first? The red one, that is my little r. I keep going. What curve do I hit second? That one's going to be my big R. Okay. So little r, we'll say, is closer to the axis of revolution. Okay. Are the colors reversed in the 3D one? Yeah, I think they are. That's unfortunate. Let's kind of test out this theory here, all right, on the actual sort of 3D picture. When I think about my axis of revolution, if I sort of go from my axis of revolution up, I'm going to hit the x cubed one first, and then I will hit the x squared one. Okay, so whichever one you encounter first, that one is closer. And the one that you come to second, that is the one that it has a greater distance. Okay. So knowing all of that, we need to figure out how to set up our integral. Okay. So we've got volume equals the integral of area. That we know, we've been doing that a long time. Volume is the integral of area. Are we thinking dx or are we thinking dy? Right, maybe let me zoom in a little bit here. Are we thinking dx or are we thinking dy? Right, we have one vote for a dy. Any other thoughts? We have one vote for a dx. Ooh. Okay, well, it turns out in this case, majority is correct. Okay, and let's kind of go back to this for a moment to envision this. These purple lines that I drew, they are perpendicular to my axis of revolution, and I'm stacking them along the x-axis. Okay, so I'm stacking these along the x-axis. You can think about this like, see how we kind of have a little donut here? Right? We have all these really, really flat donuts and we're lining them up along that x-axis. Okay. And so because we're lining them up along the x-axis, we're going to go ahead and say dx in this case, right? But the reason why we can say dx is because yes, they line up along the x-axis and the purple line is perpendicular to our axis of revolution. Okay. So you got to see the lining up along the x-axis and those purple lines have to be perpendicular. Okay. So we do have a dx here. Now we have a hole sort of in the middle of this funnel. Okay. So like this part right here, this is all empty space, right? And so when we have that, we need to think pi, the integral of big R squared minus little r squared dx. And our bounds in this case, well, we start the circles at 0 and we go all the way until 2. All right, and 0 and 2 are those x values that I believe it was, oh, I forgot who it was. It was Marissa who said, hey, let's set our equations equal to each other. We get 0 and 2. That means we start our donuts at 0 and we count all the way until 2. Okay. So that's how we know what our bounds are. But what can we put in for big R and for little r? right? So let's get that all on one page. What can we put in for big R and what can we put in for little r? Let's see. Big R is 2x squared and little r is x cubed. Yeah, exactly. This one has actually been one of the nicest questions we've encountered because as soon as we picked what our big R was from our picture, we actually had our equation in just the right format already. In fact, it was already 2x squared. So it wasn't like it was in terms of y and I had to change it to x's. It was already with x's. And so that means these two folks are exactly right. Everywhere I see a big R, I'm going to put 2x squared. And everywhere I see a little r, I'm going to put x cubed. Right? And so we'll get pi, the integral from 0 to 2 of 2x squared minus x cubed dx. Yes, no, maybe so. Nope. All right, that is a mistake that I will hope that nobody makes on the quiz or on the exam, right? Because what we have right here, we have r equals this. And so what we need to do is we have r squared. We need to make sure we square that. Perfect. And same thing over here, x cubed also needs to be squared. Okay. And so I hope that by making a show of this mistake, that is something that we can avoid. All right. I know it's super common, but I would like that to maybe be common for everybody else, but not for us. Okay. All right. Now I am going to set up this next part right here. And then we'll, skip a few lines. I'll tell you what your goal answer is. But shockingly, wow, what is happening? Shockingly, one of the most common mistakes after what we just highlighted as one of the common mistakes, but this is another common mistake. What are the mistakes? Because a mistake in any of the first few lines are pretty fatal. Like they mean that you're definitely not going to get the right answer, right? Okay, right. You were spot on. I did 2 plus 3 and I got 5. Why is that wrong? How come I can't add my exponents? I thought when we have exponents in the same base, we just add them. Yes, we are supposed to multiply. So sometimes I have folks who look at something like this and they're like, I can't remember my exponent rules. And I will say this, especially if you're on an exam or something, and maybe not for this class, but like in any future math class that you take, you can't remember what x squared or x cubed squared is. Think about what it means. X cubed squared is the same as x cubed, wow, times x cubed. I bet if you take 5 seconds to write that out, you'll know that it's not going to be x to the 5th, but it's going to be x to the 6th. Okay, so if you know that this is a mistake you tend to make or that you're always confused on, take 5 seconds, write it out. I bet you'll be able to prevent that. Exactly, exactly. Okay, now great eyes for that second mistake here, right? A lot of us are like, well, I can do that. 2 times 2 or 2 plus 2, I don't know, but either way it's 4, so it's fine. But we know it should be 2 times 2. And we get so excited, we forget about distributing to that coefficient as well, okay? And so we really want to make sure that we are clean with our algebra, and we're going to get 4x to the 4th minus x to the 6th dx. Okay. So once you have that, your integrals should be power rule, and then plug in your number. Okay. So I will leave you to find your antiderivative, plug in your bounds, and at the end, you should end up with 256 pi over 35. Okay. So one more question on the washer method, or the situation where we have like a donut looking shape. Okay, like a regular donut, no filling in the donut, just a regular donut with a hole in the middle. Okay. On next week's exam, you can expect that I'm going to be asking you to set up a lot of things. Okay. In other words, I will want you to be able to show me what is your big R, what is your little r, and tell me how you know. So when I ask these questions in class, I'm not just asking them to be like, oh, are you paying attention? Gotcha. I'm asking you because I'm telling you these are going to be similar to questions on the test, right? That on paper, the work, that's one thing, but asking you to tell me, how do you know this is true? How do you know that's true? It's going to definitely be an important layer for this exam, okay? So let's try a couple more examples with this before we take a break and shift gears. All right, so let's zoom back in. And let's take a look at something that is almost always some power of 2 pi. There should be a pi because we're looking at area, right? And all of our areas, since they're circles, they're going to have a pi in them. Yeah. Question for you all, though. Every time you, tell me if this statement is true or false. Every time you volume, you should end up with, you should pi in, right? So every time you find volume using integrals, you should have a pi in your answer, true or false. All right, I have guess for false, false, false. Okay, if it is false, yes, tell me why that's not true. Okay, because we might be looking at rectangles, right? If we're looking at rectangles, are we going to have pi in them? What would we use when we're finding like rectangles? So pi is usually associated with things like circular stuff. So if you're looking at the questions, if they say something like rotated, then you're thinking, oh, I'm going to have some circles, so then my answer should have pi in it. But if you think back to last week, and we're looking at questions where it's like, here's your base, you have rectangles coming out of this, or you have triangles coming out of this. If you have a pi in your answer, that's probably not the right area formula, okay? Exactly, exactly. So we want to be really careful about that. Sometimes when we go through these kinds of questions, people are thinking, well, everything has a pi, so I'm just going to stick a pi at the end on my answer just to, I don't know where it came from, but I'm just going to put one here anyway. And so we really want to be thoughtful about like what shape of air are we taking the area of, right? If we're taking a shape that is circular, yeah, you should have pi in your answer. But if we're looking at having rectangles or triangles, then we probably don't want to have a pi there. Okay, so go back to those formulas, think about which ones should have pi, which ones should not have pi. Okay. All right, so question 12 has a few typos. Determine the volume of the solid obtained by rotating the portion of the region bounded by y equals x squared minus 4x and y equals 0 about the y-axis. Okay, so let's make those changes to our question. So determine the volume of the solid obtained by rotating the portion of the region bounded by x squared minus 4x and y equals 0 about the y-axis. Okay. So let's set this up. Let's start with our diagram. Okay. We did look at this function the other day, y equals x squared minus 4x. Can someone remind me how we can sort of sketch that function? Like, I know we know it's a parabola, but how can we be more specific about sketching that? Factor, find the x-intercepts, and perhaps find the vertex. Okay, so let's factor out an x, so x minus 4. And so we get x equals 0 and x equals 4 as our two x-intercepts. Now, parabolas are symmetric, so that means the vertex is going to be exactly halfway between those. And so we'll end up with something kind of like this. And we'll say that this is 4. Okay. Now we also have this function y equals 0. Y equals 0. What might that look like on our graph? Y equals 0. That's going to be our x-axis precisely. So y equals 0 is going to be somewhere here. Okay. Now, the last thing we have is our axis of revolution. And we are revolving this shape this time around the y-axis. Okay. So since I don't have fancy computer generated images, what I'm going to do is draw my little arrow. So I know that I'm revolving around this axis, but I'm just going to draw a reflection of what I see on the right-hand side. I'm going to draw that on the left-hand side. Okay. Now, if I wanted to find this volume, and I wanted to use washer method, which we've been using. My purple lines, how do they have to be in relation to my axis of revolution? when I draw those purple lines, they have to be perpendicular to this. So I would have to draw them going sideways. Like this would be a purple line. This would be a purple line. This would be a purple line. What's my big R? What's my little r? So big R equals, little r equals. Now I might say, well, like this part of the curve could be my big R, and then this part of the curve might be my little r. But that seems like it might get really messy because I have one equation and I have to take one equation and somehow split it into two equations. What are our thoughts here? Any ideas on how we might be able to adapt what we know to find the volume of this shape? Maybe writing it in terms of x. Okay, let's see. All right. How would I solve for x? So to isolate x, what would that look like? Okay, so we factored before x minus 4. And so we could divide. So y over x equals x minus 4. Y over x minus x equals negative 4. How do I get that y over to the other side? I just want x equals. I don't want x mixed in with a bunch of things. I multiply by y, let's see, y squared over x minus yx equals negative 4y. Oh, divide by y, okay, so 1 over x minus x over y equals negative 4 over y. Ask the y to leave. Yeah, maybe we didn't say please, right? We're like, could you please leave? This looks kind of frustrating, huh? I hope we're looking at this and being like, I don't understand it. I understand that we need perpendicular purple lines, but then I don't understand how to get the R, my big R and my little r. Very interesting point. I think that we have thought about this in the past. That's worked for us in the past, where we isolate the x and then we're able to get some equation that we can use. I don't know that that is helpful in this case though, right? So we're going to leave this question where it is right now, okay? But a question like this, if you get to the test next week and you're working through and you're like, I cannot find my big R and my little r, perhaps it would be in your best interest to try the method that we're going to learn after break. Okay, so if you are trying to make this work and it's just not working, like it's so hard, you can't isolate the letter you want, the picture doesn't work the way you want it to, then we're gonna have to try a different method. Okay, so I'm gonna leave a little note here where we say, in cases like this, try shell method. Okay. If we divide it by x, we get y over x equals x minus 4. Yeah, so we're sort of back at that same place where Ethan was trying to take us in that before. Okay, so I see a question. How do we know when we should reflect the graph? We're not reflecting it, we're just trying to draw a three-dimensional situation, okay? Which is really hard to do. So if I were to do this in like the little laser pointer thing, we have sort of like one really big circle out here, and then we have like smaller circles in here. Like that's really hard to draw. That's why those computer generated diagrams are so nice, because they help us see that. But when we are talking about rotations and it's hard to draw a 3D thing, then I draw the reflection to help me start to imagine that. Does that make more sense? Yeah. Okay. All right, so let's finish up one last question where I promise you we can actually use the methods we've been learning in this section, okay? And that will be example 13. So example 13 says, determine the volume of the solid obtained by rotating the region y equals x squared, or x equals y squared, and y minus x plus 2 equals 0. And we are revolving it about the y-axis. And so as soon as I see that word revolve, in my head, I'm thinking, once I sketch the graphs, I'm going to draw that reflection on the other side of the y-axis just to help myself imagine what this might look like, okay? So as I'm setting up the grid, tell me about y equals, oh my gosh, I can't read. Tell me about x equals y squared and y minus x plus 2 equals 0. What do those look like? All right, so let's do our axis of revolution. So we know where that is. And yeah, y equals x squared is indeed a sideways parabola. Love the specificity there. We know that it is opening to the right, okay? So for those of you who are like, how did he know that so quickly? When we're thinking about parabolas, okay, if we have regular y equals x squared, we know that that opens up. And when we think about things that are like x equals something, in general, the positive things open to the right and negative things open to the left, okay? So if we were to sketch that out, we would have sort of a parabola facing that way, okay? All right, tell me about, this one, y minus x plus 2. All right, what shape is this? Let's just be a little explicit about this. What shape is this? It's a line, I would agree. All right, And let's think about how would we know how to graph this? Like generally when we graph a line, we say, here's the x-intercept, or here's the y-intercept, here's the slope, and we plot.
We could subtract y and then multiply both sides by -1.
We could do that. We could certainly move the y, right? But what might be a little bit quicker, let's just take these two and move them to the other side.
That works.
Okay, so if the y is already positive, let's keep it positive, and we'll just move the other two pieces, and we get x minus 2. Right? So from here, I hope we remember that the slope is 1, and our y-intercept here is -2. And so we end up with something that's going to look sort of like this. Okay. So yeah, if I kept drawing, I would get to -2 on the y-axis, and that would be my y-intercept. Now, I do want to find the intersection. Okay. So I solved for y because that's what we always did in middle school and high school. We always got y by itself. But let's look at this for a moment. We have x equals y squared. Maybe instead of getting y by itself, what if I got x by itself and gave that a try? I would have x equals y plus 2. Okay. X equals y plus 2. Now I could write this either way, y equals x minus 2 or x equals y plus 2. Either way, how do I find the intersection between the pink parabola and the green line? Set the y's equal to each other. I could do that. I would say there's probably a more efficient way to do that. If I set my y's equal to each other, I'm going to need some square roots. Okay, so let's set the x's equal to each other. All right, it's not wrong to say set the y's equal to each other. Okay, however, in this case, if I do that, I'm going to have y equals a square root. I don't really want to deal with that. So I'm going to take this pink equation. I'm going to take this version of the green equation. They're both equal to x, so I'm going to set them equal to each other. And so I'm going to get x or y squared equals y plus 2. Okay. And so if we're trying to set this equal to 0, y squared minus y minus 2 equals 0. All right. This looks manageable. What does this factor into? Yeah, so y minus 2, y plus 1. All right, and we should get y equals -1 and positive 2. And that's great because that means I don't know what the x value here is, but I know that the y value is -1. And same thing up here, I don't know what the x value is, but I know that the y value is 2. Okay. Now, it might bother some of you that there are blank lines there. You can certainly find the X values if you want to, but I will tell you right now that if you find them, we might not actually use them at the end of the day. So you're welcome to find them if that makes you feel better about, you know, filling in those points over there. But in the big picture of this problem, I don't know that we're actually going to come back to those values. Okay. So now that we know from example 12 that there's this other method floating out there, we need to be careful about what we're trying to do. So here's our axis of revolution. If I want to use the method that I know so far, which is washer method or disk method, which direction should my purple lines be? Yeah, we want them to be perpendicular to that yellow axis of revolution. Okay, so see how these red ones right now are all perpendicular to that axis of revolution. I'm going to go ahead and draw them in with the purple lines. Okay, so like here would be one, here would be one. All right. Now, from drawing these purple lines, are you thinking pi r squared or pi big R squared minus pi little r squared? Which one are we thinking? Just regular pi r squared or pi big R squared minus pi little r squared? So pi r squared or pi big R squared. All right, I see many votes for pi r squared. Okay. Well, what we haven't done yet is draw our reflection piece, okay? If I were to draw the reflection piece, and let's see how this goes, I might end up with something like, this is clearly a not great reflection. Oh, actually big R, little r, because we will have empty space in the middle. Okay. So as soon as I draw, like, this is the part where I'm like, I can't just cover up something that I drew on the board. So imagine I didn't draw this, right? When I look at the right-hand side, that picture is solid, right? Like all of this is solid. There's no holes here, but that's not the shape that I'm trying to find the volume of. And as soon as I draw that reflection, what I see a little bit more obviously is that, like up here, I would have something kind of like this. All right, so I'll leave that there for a moment so you can kind of squint your eyes a little bit and see this three-dimensional washer hanging out there. If I drew one at the very bottom or close to the bottom, I might have something kind of like this. And so remember what we said, this purple line, if it doesn't go all the way to the axis of revolution, guess what we have? We have an outer radius and we have an inner radius. Okay. So in this situation, we are not using disk method because we're going to end up with a bunch of donuts, regular donuts, donuts that have holes in the middle. And so we need to compensate, like all of this space is empty. All of this space is empty. Okay. And so for that reason, we want to choose pi big R squared minus pi little r squared. Okay. So I'm really glad that folks guessed what they thought, and that we all were like convinced that maybe it was going to be the pi r squared, just regular. But if this part was helpful, I would encourage you to do that part, right? Help yourself out and draw as much as you can to support this idea of like, what does this look like in 3 dimensions? Okay. And so with that, let's see if our trick of finding the big R and the little r work even when we're going sideways. So I'm going to draw one of these like lines, right? I'm going to draw one of these lines. The first curve I come to will be my little r. And the second curve I come to will be the big R. Okay. So if I pick a point up here, first curve is the pink one. That looks like my little r. Second curve is the green one. That's going to be the big R. Okay. But let's do a few more test points to make sure. Start down here, pink, and then green. Start up here, pink, and then green. Somewhere in the middle, start here, pink, and then green. Okay. That means that my big R is going to be the green function and my little r is going to be the pink function. So big R will be the green function, little r will be the pink function. So let me pause here for a moment because I just want to make sure I've given you enough time to process why it's not the pi little r squared. How are we feeling so far about what's up on the screen? Is it a little bit more clear why we have some holes in the middle of our shape? Good. One of the many nights that I did math with my dad over the kitchen table, of course there were tears involved, but I think I like could not understand a problem. He's like, if you don't understand it, just draw a bigger picture. And I was like, that's not going to help. But then I drew a bigger picture and I was like, okay, I get it now. So it may or may not help, but I think we all kind of find things that work for us. So this is one trick that I've sort of learned over the years, but there might be other ones that speak better to you. All right. Yeah, so many decisions to make, right? So many decisions. Okay, well, let's set up our integral. I'll tell you where you want to be at the end for your solution, but let's see what we have so far. We have an axis of revolution, and we have lines that are perpendicular to that. That tells us we're going to use this method. Now, with this method, if we are stacking along an axis, that axis tells us whether we should be dy or dx. So in this case, because we are stacking up the y-axis, we're going to say dy, all right? So volume equals the integral of area dy. I'm going to go ahead and pull the pi out into the front of big R squared minus little r squared dy. And since we're dy, that's why I was like, you can find that x value if you want to, but I actually don't care what it is. I want to know what the y value is, because that -1 is going to go right down here. And then that +2 that we found, that will be our top bound. Okay, so -1 on the bottom, +2 on the top. Now, let's not make that mistake that I've been like, don't make this mistake. And we're going to put the green equation in there first. So which one of these two versions do I want? The one on the left or the one on the right? See, one vote for right. What do we think? Not sure. All right, well, I agree with David. I think it should be this one, the one on the right, because we want to have y's in our equation. Okay, and so we'll have y plus 2 squared, so that's our big R squared, minus, let's see, what was our pink equation again? X equals y squared. Great, so I'm going to have y squared squared. Okay. Definitely in this case, it's so easy to forget that second squared because we're like, we already have a squared. Why would we need to square it again? Okay. What is the mistake you think will happen here? You guys have been so great about identifying these mistakes. What do we think could go wrong here? Not foiling, right? But we know better. We're not going to fall for that. We're going to make sure we foil. We're going to get y squared plus 4y plus 4 minus y to the 4th. Right. Now, one thing I noticed, and this was not a very common thing, but there are a few of you out there who sometimes don't look to see if there are like terms. Okay. Now, in this case, there are no like terms. But if there are like terms, I would combine those first so that you can save yourself a little bit more on the back end when you plug in the number. Okay, so good sort of rule of thumb, try combining any like terms you can before you take your integral. Okay, before you take your integral. And so at the end of the day, you should end up with 72 pi over 5. And we anticipated a pi in our solution because we had a bunch of rings that we could stack up. Why would y squared and negative y to the 4th combine? Why would they not combine? Why would they combine? What would they make if they combined? Yeah, I think it's sometimes we're like, oh, I don't know, I distribute the powers or whatever, but we just want to be super careful, right? We're looking for like terms when we're adding and subtracting. Yeah, exactly. The degrees have to be the same. Good point. Good point. I love it. Yeah, exactly. If we could add these all up, we would have no polynomials and life would be so much easier, but it would also be much less interesting. So, all right. Well, this seems like a great time for a break. Okay. I will let you know before we go on break. You are welcome to take a look at 6.3 or this part right here. Okay. This rotation around other axes. I will not test you on these. If you were planning on going fairly far in math, it might not be a bad idea to look over these, but most of the questions that you encounter will be of the variety that we've already looked at. Okay, so this one, don't worry about this for the exam. But there are some more pictures you can look at for, help visualizing things, or if you're wondering like what might be incorrect or what might be how we take care of, different axes of revolutions, this is sort of an interesting piece to look at, okay? So more examples, more examples, more examples. But if you never scroll to the end of the notes, today there is a surprise for you. So there is I don't know how many of you have an air fryer or access to an air fryer, but last year, you know, when everybody was in lockdown and things were very lonely, and I was like, oh, my roommate has an air fryer. And it turns out that there is a link for literally 4-minute air fryer donut. If you go to the store and look at some Pillsbury dough, you know, the kind in the blue can, that's what they use. I think it's maybe even their biscuit dough. Turns out, if you cook that in the air fryer for literally 4 minutes, and then you sort of like roll it around in some cinnamon sugar, pretty tasty snack. I can definitely vouch for this. Okay, so if you're not even going to look at the rest of the notes, just look at this one piece, go check out that link. I'm not an influencer, but I just really like donuts, and I thought this was really fun. So okay, now yeah, now let's take a break. All right, it is 10:40, so let's be back at 10:55. All right. Yeah, I don't care if you don't ever use the calculus again, but at least you will have a donut recipe that you can, like, you know, impress people with. All right, so let's